Thank you, Aline, and thank you, Tema, for organizing the event and for inviting us. I do apologize for not being there in person. We had to have an unfortunate last-minute change of presenters. So due to the short notice, it was just not feasible for me to be able to travel to Turkey for this program. But I am glad that we're able at least to share the next few minutes together and talk a little bit more about some of the things that, in particular, Quadro and Fitzpatrick have been doing over the last few years. So we're going to talk a little bit about technology. But before we do that, just a quick introduction of who I am. I've been with Quadro since 2005, so the almost 20 years in March. I know what everybody's thinking. I must have been 14 when I started because obviously, 20 years have gone by. But I've had a few roles over the years, mostly in product management, and then the last little while more towards the application side of the business, how to support customer applications. And right now, our new venture is to develop an internal academy to take all the knowledge from all those years and to train all our internal, external partners on our technologies and how we can improve our customers' day-to-day activities. Quadro is part of a bigger organization called IDEX Corporation. And within that group, there is a smaller subset of companies that are all related to each other because we sort of manage the same type of applications, and that is MacCon, Fitzpatrick, Microfluidics, and Steridos. Some of our customers that we work with just about every customer in the world, in the pharmaceutical, food, nutraceutical, and the chemical and cosmetic industries. So today we're going to talk about some of the things that Quadro and Fitzpatrick have been doing over the last little while. So we're going to talk about some changes, some improvements, some new developments, which have been really, really exciting for us. So since 2016, we've actually been sequentially introducing new products, new improvements to existing products. And we're going to touch on a few of those this morning, just so that for those who are not aware of some of the things that we've been working on, I think this will be fairly interesting. So one of the things that we've done is we have made an entire platform of our underdriven conical mills part of what we call the exchangeable milling technology. So all the way from the lab units, the SLS, that's the bottom right photograph, where you can interchange 4 different heads. And then we go to the medium production, the pilot or medium production scale, and then all the way to full scale production mills. And they all carry the same sort of technology, what we call the smart detect, because it sounds really nice from a marketing perspective, but it is a way for the machines to detect which head is in place. So this interchangeable technology, we started in 2016 to have our product lines, and then we've been adding to the portfolio by switching all our production machines to that same technology, which is really good because then you can take a single drive, and then if you need to do a finer milling application where you need a Fitz mill head, then you can put the Fitz mill head on it. If you need to do a coarser application, you can put a co-mill mill head in it. If you have to do a security screening, then you can put a flexive head on it. And again, this goes from the lab all the way up to production scale. And then within that new technology, or sort of this new package that we have done a lot of changes to our actual machines themselves. So one of the things that we used to do is when somebody wanted to have a machine that was clean in place, not wash in place, because for us, washing in place, you have nozzles that spray inside. It gets everything wet. That's what wash in place. It may clean most of the things out, but clean in place means that you can clean, you can dry, and then you can run your next batch without opening the mill. That's what clean in place means to us. So we've made some changes to our clean in place technology to make it actually a lot more versatile, a lot more flexible for our customers. Another big change, and I'll talk in a little bit more detail in the next couple of slides, is we've gone to a greaseless gearbox. I'm going to talk a little bit more about what that means. We've introduced a complete new design of screens for dry milling. And we've made all our housings, except for the Fitz mill, to be PSR rated. So we have now made that sort of standard across the both the coal mill and the flex sift. So what does that mean as far as, for example, the cleaning place? I just finished catching the previous presenter talking about excuse me, OEB bands and OEA levels. So with our mills, we have always had the ability to have under 1 microgram per cubic meter OEL level. So usually OEB5. It's something that our mills can do as standard. And we actually have some SMEPAC tests where we are down into the nanograms, like 50, 100 nanograms on average with our mills. But our standard is just under 1 microgram per cubic meter. So if you look at the top right corner, those were the screen designs that we used to have for cleaning place. So we had an O-ring capture at the top, O-ring capture at the bottom, whereas the new design is actually using standard screens, the screens that all customers would have. And now if you look at the bottom left image, we have transferred those two O-rings to the housing and to the infeed chute. So what this does is, previously, if a customer wanted to have a cleaning place mill, they had to buy a different head, like a different milling housing. They had to use those special screens, which were not interchangeable with a non-CIP mill. So either you did CIP or not CIP, you couldn't do one mill that could do both. And the cost of those screens is about 3 times the cost on the top right corner as it is on a standard screen, because there's quite a bit of work to weld that top flange to make sure that the screen doesn't warp. It's actually a very, very time-consuming process. So that's one of the things that we did. We decided, okay, let's make our screens so no one has to get any special screens. They can use screens from other machines. They can use it on the new machine. Now, all they have to worry about is that the fact that we've pre-designed the CIP features into the actual housing. So the other example that I'll show here is we've actually have tapered the inside of the walls of our machines. And what that does is, as you're milling and powder gets stuck to the walls a little bit, we wanted to make sure there were no right angles at the very top of that housing, so that by putting a taper, as you're cleaning, it allows out the cleaning fluid to actually travel easier on that inside wall because it's tapered towards the bottom of the housing. So it keeps having tight areas where you have powder accumulation, and it also allows for the cleaning. That's just one of the many things, because the gearbox is a little bit different, the impeller is a little bit different. There's other changes as well, but we've now made them all those as standard. The other big change that we did is we introduced a greaseless gearbox, which means that we are running a machine without any grease. Now, all the previous machines have FDA-approved grease. There's a small amount of grease that is used in the inside the gearbox mechanism, but we switched to a greaseless gearbox for a couple of reasons. One, obviously, is to maintain product safety. So if there was an issue with the very lip seal that seals the shaft from the mechanical side, we wanted to make sure that there was no chance of grease coming into the product. But by doing that, we did a couple of also big improvements. One was the sound, because one of those two gears is a composite gear. Composite gear that's been used in the aerospace space industry for many, many years. So we're adopting technology that's been proven in very, very harsh environments, and we're now putting it into the actual gearbox. So we've dropped the sound of our machines significantly, about 5 to 10 decibels on average. But the other thing that it's also improved is our temperature. So as we run our machines, because you have a gearbox that has to be packed with grease and it has to be perfectly done, you actually had a higher increase in temperature of that gearbox. Now, eventually, this is a 2 or 3 hour test, 2.5 hour test, where you see the orange line continues to increase. Eventually, about after 3 hours, it levels off the temperature. But as you can see, it's about 70 degrees Celsius, which is fairly warm. Whereas with the composite gear, we level off after about a half hour, 45 minutes, and then it just sort of starts to then eventually decline in temperature. And all that temperature, obviously, what we don't want to do is transfer heat from the gearbox to the impeller to the product that's being milled inside. So those are two big benefits. And of course, as I mentioned, the other one, of course, is the very lip seal, which is the section up here. I don't know if I can quickly section. That is a section that if that seal were to be damaged, then you may have product coming in, and that obviously is not good for the mechanical side. But if there's grease inside and say water comes in, then that grease could eventually make its way out. And again, we want to obviously have mitigated that by going with a glueless gearbox. We still need to have customers check the bare lip seal, and we have ways to make sure that that seal is always good. It's always making good contact. But just in case something were to happen to the seal during cleaning, sometimes operators are scraping stuff and they damage the seal. So things can happen to it. We want to make sure we make any other next steps. Make sure they don't have any oh boy, I have to. Sorry, I got to delete that. And I didn't realize it's going to stay on place. Eraser. Look at that technology. Perfect. There. The other thing that we did is we have been talking with customers for a long time, and one of the things that we sometimes see in the industry is product blinding screens. Now, this is not our machine. This is a machine. This is another conical mill. And we have had customers that are dealing with products that are susceptible to temperatures that may tend to blind. And we kept hearing from customers saying, is there anything that can be done to prevent powder from sticking to the walls from actually blinding screens? So what we did is we actually have patented a different design screen. Now, this screens are compatible with older machines as well. So if you have an older coal mill, U5, U10, or U20, you could use the screens, but we have this, what we call the high efficiency screens. And we patented this back in 2020, and I had no idea how long it takes to get a patent. This was like a 2 or 3 year process to get patents on things. It was a very, very time consuming, but what are the main things that we were able to achieve with high efficiency screens are we were able to reduce the temperature that's being generated while milling. And the reason why we call them high efficiency is because it allows powders to flow through faster. So the faster a powder flows through the mill, the less time it stays inside the mill. So the less time it generates heat. So by getting powder out faster, we drop the heat. And then by getting out powder faster out of the mill, we actually increase the capacity. And the average capacity of the high efficiency screens is about 50% than the legacy screens and previous screens. For some screens as high as 60, even 65%. But the average between our screens is about 50%. So how does it work? And I try to explain the patent, and you can find the patent on the internet. You can download it, you can read it. If you read a patent, it's really hard to follow what it says. So try to explain what we're doing. So I took a photograph of our high efficiency screen and then close-ups of the holes near the bottom and the holes near the top. And what we've done is we've actually changed the number of holes that are on the screen, and they get closer to each other the closer we get to the top of the screen. So as the screen goes from top to bottom, we actually have a gradual increase in open area between the bottom of the screen and the top of the screen. And why did we do this is because the screens are angled, but they have a 60-degree angle. And what happens is as the powder and as the impeller is rotating, the powder tends to travel towards the top of the screen and then it goes out. So most of the milling happens in the top 1/3 of the screen. So by us providing a higher percentage of open air near the top, we actually have increased the ability for powder to go through the screen faster. Now, we haven't changed the whole diameter, so that was key. So if you had a 2mm screen, it is still a 2mm whole screen. Every single hole is still the same diameter. We just added more holes at the top of the screen. So that's what the high efficiency screens do. We ran some CFD analysis to see what that actually meant before we started doing too much more work on them. And here's two images of a legacy screen on the middle there, and then a high efficiency screen on the right. And this shows the airflow. And the darker blue shows slower. And then as you get to a green and yellow and red, it shows a higher velocity that's being generated inside. And as you can see, the one on the right-hand side generated a lot more velocity, which meant that a lot more product will be able to get through. So we did this airflow pattern. And then we also looked at the mass transfer. So this is basically the equivalent of capacity. And it has the same scale. The darker, the slower meters per second velocity it is. As you get close to red, the faster it is. And you can see where the milling area is. So there's a picture there of the impeller near the middle. And you can see the blue color, which means that it's slower. There's a little bit of green on the side and then green on the edges. And then most of it slows down. Whereas on the high efficiency screens, it is mostly that green color in the middle, and we even have some red, which means that we're going very, very fast. So the mass transfer of the high efficiency screens was shown that on the CFD analysis that they would generate a higher throughput, a higher capacity. So then we ran a number of tests, and I didn't put every single test on this chart, but I just wanted to show you some of the things that we tested. We did some placebos, citric acid, acetaminophen, some products. We kept the impeller profile the same, so we kept the same impeller type, and we kept the same speed. So we're not changing any variables other than we went from a legacy screen to a high efficiency screen. As you can see, the part number is identical except for the letter H. And we have that for high efficiency, but the rest of the numbers still tell us 1 millimeter, 1.6 millimeter, 1.9 millimeter, because again, we did not change the actual diameter of the holes. When we started plotting the data, this is where we came up with this 50% improvement. So as you can see, some screens and some products behave a little bit differently, but on average, it's about a 50% improvement on capacity on the 1 millimeter screen. And on the 1 millimeter screen, we're having about almost a 30% drop in temperature rise. We did some things with other screen sizes. On this one here, we had a 33% increase on the 1.6 millimeter with a 43% decrease in temperature. And then the last example, it's a 1.9 millimeter, 36% increase in capacity and 19% decrease in temperature. And again, we did a whole bunch of other tests as well. The one item that customers always want to make sure that when you change technologies, you're not changing what you're trying to do. So we also wanted to make sure that the particle size distributions were not going to be affected by us changing how powder flow through the screen. So here we have a couple of examples with overlapping curves where we show the legacy screen, the high efficiency screen, and they're basically identical. And on the left-hand corner, I have an excerpt from the FDA that talks about what are usually the upper limit, lower limits that are acceptable, so that you know that if your powder is within that range, you're going to get good tablets. So you have validated your process that says, as long as my distribution is within this upper and lower limit, I know that when it goes to the tablet press, I will be able to make good tablets. So again, we did not want to change particle size distributions, but we wanted to be able to provide customers with an option for their product, especially if it's heat sensitive. The next section of our morning is going to talk about a little bit of what we just talked about with the high efficiency screens, but a bit more of a overall perspective of our technology and how do you ensure that whatever you do at the lab scale with a lab machine can be scaled up to a production. So there's different parameters that will affect your milling. The design and the tolerances, that's something that we as a company obviously have, and that's one of our differentiated features that we have versus other technologies. How you integrate it, how you feed it, the materials of construction, surface finish, all those things will affect particle size. But the things that most customers have more control over are the tooling selection, we call the screens and the impellers, and how fast they're rotating, how the RPM that we're using, and all these have an effect on the particle size. So we have an example here of a wet granulation. So whenever you have a wet granulation product, just before you do the drying. If you put it through a mill, one of the big steps that we always recommend customers, and there's papers on this. I just did a blog on this as well on LinkedIn, but there's lots of literature that talks about the benefits of putting a mill after a high shear mixer. And the main reason, as you see in this picture, is when you finish granulating, you will be left with bigger and smaller. Sorry, I'm trying to find my pen here. There we go. You'll be left with some bigger lumps, and then sometimes you'll have smaller, medium size, and then you have some very small ones. So when you have that, and then you're going to put that into your fluid bed dryer, if those lumps are not removed, what will happen is you will have a product that will be either over dried. So if you're drying for say 30 minutes, 40 minutes, and you have different size granules going into the dryer, the smaller ones are going to be super dry, and the big ones may still have a soft center. Or if you haven't sure the soft center is not there, then the smaller ones will be even harder because they've been there longer being dried up. And there's all kinds of papers that actually show that if you do that, you actually will generate more fines during the dry milling step. So the very first thing we do is when somebody's using a high shear mixer, we will recommend them to use square or slotted screens with a square arm impeller. That is the standard. And then within these two types of screens, we have different sizes. So we have as small as 6.4 millimeter all the way up to 25 millimeter. And the size of the hole really depends on the characteristics of the wet granulation. The heavier, more dense granulation may require a slightly bigger hole than the non-so, the ones that are drier. Drier one, you may be able to use a 9.5 millimeter whole screen. Because the goal of this is not to make small particles, but it's to make every particle that's going into the fluid bed dryer to be as equally sized as possible. So that's a big difference between dry milling and wet milling. Here, we're not trying to get small. We're just trying to get everything that's more evenly distributed before it's into the dryer, so you have good dry product. Then the product goes into the dryer, it gets dried up, and now there are two primary places where you would do any milling. And again, the goal of milling is to get a really good particle size distribution. Usually 20 to 200 mesh or 75 to 800 micron is the industry standard. And there's again lots of papers published on these benefits of having that range, because you don't want to have 100% of your product to be say 300 micron, because then you wouldn't be able to make tablets. You do need to have a distribution of finer and coarser, so when the tablet press is pressing that powder into a tablet, the smaller, finer product goes in between the larger one. The larger one can then be shaped into a tablet, and then you have a robust tablet. So you do need to have a distribution, but you also don't want to have a very wide distribution where you have a lot of fine products and a lot of coarser products. Then you wouldn't be able to probably make a good tablet. So it's a fine line between too much and too tight. So what are some of the things that happen when you do actual milling steps is you can control the particle size or your distribution by the hole size. So the bigger the hole, it's obviously the coarser the particle size distribution is. And then the smaller the hole, the smaller the particle size. But interestingly enough, as you go smaller hole size, you also tend to make a wider distribution. And as you go to a smaller hole size, the open area percentage drops a little bit, which means that there's a little bit more steel in between every hole, and that helps to generate a little bit finer powders. So this is one of the things that the diameter will do to your particle size. So again, we're showing the same product being milled with a smaller screen, larger screen, and evidently that makes a difference. The one thing that I always found that is very interesting is when you have the same diameter hole size, but you have a different profile. So the two main types of screens that are used in the industry are either a round hole with nothing special on it, or a rasp or a grater screen that looks like a cheese grater. Those are the two main types of screens used in dry milling. And there is a significant improvement when it comes to your particle size distribution. So when you look at those two curves, they're both done with the same size screen, a 2 millimeter round hole screen for both of them, but one is a grater in the top and the one is a round in the bottom. And if you can imagine, as your powder comes into your mill and the impeller is rotating, The one with the grater basically is pulling out powder much, much faster. So the faster the powder can come out of the screen, the tighter the distribution is, the coarser it's going to be because you're not generating as many fines. So the opposite is the longer you keep powder inside your milling chamber, the finer you're going to get it because it's being recirculated and hit over and over and over and over again. It also generates more heat because the more time you keep powder inside your screen, the more heat it generates. But the greater screens, their main goal is to be able to get you a much, much tighter particle size distribution. So that is one of the big advantages of the greater screen. And also by doing that, not only are we getting a tighter distribution, but capacity can sometimes being increased by as much as 100%. Like you can double your capacity between a round hole screen and a greater screen for some products and some screen sizes. So it's a big plus. Then the additional big plus, as we talked about the high efficiency screens, is that we can now even take what was really good between a greater screen and a round hole screen and now go greater high efficiency. We actually even increase that capacity even more and we reduce the heat even more. So here's an example of the exact same screen hole size, 1.6 millimeter round, 1.6 millimeter greater, 1.6 millimeter greater high efficiency. And you can see it went 50%, 40% as you're going with the different types of screen, always with the same 1.6 diameter hole. And then on the bottom, it's the exact same steps, round, greater high efficiency, and then your reduction of heat, 20%, 50%. So there is additional advantages on the high efficiency screens, even over our standard screens. The other item that also makes a difference on your particle size distribution is the impeller profile, the shape of the impeller that's actually doing all the milling, that's actually hitting the powder, pushing the powder through the screen. We have many different kinds, but the two primary ones are a square and a round. Those would be the ones that get used for the majority of the milling applications. And again, the impellers will have an impact on your particle size distribution. And on this one here, the round hole actually is a bit more efficient in getting powder out. So the round, it acts almost like a press as it's pushing powder through that screen. So by pushing it through the screen faster, we get a coarser distribution and less heat. Whereas the square arm impeller, it sort of hits the powder more like more impact, as opposed to more grinding. So the impact will hit the powder, some goes past the screen, some stays inside the screen and goes over a little bit longer before it actually comes out. So the longer, again, you keep powder inside, the more fines you're going to generate. There isn't a huge difference, but it could be a slight shift. That's what you need in order to get your particle size perfect for your tableting needs. And then the last parameter that I think he gets sometimes overlooked is the RPM. It's the speed at which you're running the mills. So here we have an example of the same product run at 7 meters a second tip. That's the velocity of the impeller. Then we double it to 14, and then we double it again to 28. And you can see the big jump between 7 meters a second and 14 meters a second. But there isn't a big jump between 14 and 28. So there's no, the 14 is what we call the sweet spot of the mill. That's where you get the really nice tight distributions and you generate very low amount of fines. The 7 point, sorry, my apologies. The 7.1 and the 14.1 are the two top curves. So they're very close to each other. My apologies. And then the 28 meters a second, we're putting so much more energy. We're now generating a lot more fines. So when you look at the two, so the 7 is this one, the 14 is this one, and the 28 is this guy here. The faster you're running your RPM, obviously, the more energy you're putting in, the finer the particle size distribution is going to be. So the reason why I think it's interesting to look at these two curves is at 7 meters a second and at 14 meters a second, you're getting very similar particle size distributions. But the next item that becomes critical is the, sorry, I'm gonna erase these so that, there we go, is when you look at the capacity. So capacity is actually linear. And the faster you're milling, you're running your product. So here's an example of 7 meters a second on the way up to 18 meters a second. The faster you go, the higher your capacity is. So there's a fine line between your tip speed giving you a really good distribution of powder and your capacity that you need to do for your production scale. So if you imagine you're doing trials in the lab and you say, okay, I like what I'm getting at 7 meters a second. That is really nice curve. But at 7 meters a second, you're getting a much lower capacity. So you may get, this example is it's sodium potassium chloride that mills pretty easily. But you may say, okay, I'm going to get 50 kilos an hour in my lab at 7 meters a second. Now I need to go to production. In order to go to production, I have to do 200 kilos an hour. Now I have to jump like 2 machines in size to get to that production capacity. Whereas if you were to run at 40 meters a second, you have almost a very, very similar distribution. But now from 7 to 14, you've gone, on this example, from 400 to 1,000 kilos an hour. So by going a little bit faster, you're still getting your particle size distribution, but you're getting a much, much higher capacity. So when now comes time to scale up to production, then you don't have to jump so many machines to get your production scale. So there's a very fine line between your setup and what you have to do when you start scaling up to a production. And as I also heard the previous colleague talk, the proof of concept testing is critical on all this, and we encourage our customers to talk to our partners, and then our partners can talk to us, or we can talk to our customers to explain and help them how to optimize their testing at the lab scale so that it will optimize your actual requirements in a production machine. So again, those two things are very important with each other. And then what you have to do as you go from lab scale to production is to make sure that you're not changing anything, that you keep the same parameters. So you've done your trials at the lab scale. You've determined what is the best hole diameter, what is the best screen type, hole, round hole versus greater, and what is your best impeller profile. Now you have to make sure that those three are maintained as you go to the next model, the next model, and the next model. Like you have to make sure that those things are constant, because that is what the powder is going to see when it gets milled, whether it's in the lab or in production. Still going to get that same energy, that same action, that same milling being transferred from a small to a larger machine. So that's one key thing. The second step is to make sure that we maintain the tip velocity. And we can provide the formulas, but they're very, very easy. So that the goal is that if you're running a test in the lab, here's an example at 1.6 times what we call standard speed. You multiply that 1.6 times any of the other RPMs in order to get the same tip speed at the end. So as the machines get bigger, the impeller gets larger, the RPM drops, but the velocity of the tip of the impeller stays the same. That's our goal. And again, then we're transferring the same amount of energy to the milling process, no matter if it's a small mill or a large mill, because the tip velocity is what is impacting the powder, stays constant. And again, if you have any questions on scale up, you can let Tema know, you can let us know, and then we'll easily do the calculations for you if you need to. But it's a very, very easy scale up process. And what that does, it allows us to be able to confidently tell customers, you're going from a U5, you can go to a U10, a U20, even a U30, which is our largest 100-driven model. You're going to get your distributions to be transferable and predictable, as long as you keep your impeller the same type, your screen the same type, and your tip speed the same rotation, so the same velocity of your tip speeds. Then you'll be able to scale up. And then we have a very easy scale-up process when it comes to which machine to select. The math is fairly easy to do. So these are the things that, again, are important when it comes to our milling. So just to recap, we have been very busy, especially, it was interesting because during pandemic, we launched 3 things. Maybe we had more time to actually concentrate on development. We weren't traveling as much. And so we've done the introduction of our smart drive exchangeable units from lab all the way to production. And then the other big thing, of course, is the high efficiency screens that allow us to provide customers with a alternative result without changing anything. So that, if you're validated on a 2mm screen or a 1mm screen, but now you're finding that your product tends to overheat, or you'd like to have your increased capacity, but you don't have the ability to go to a larger model, depending on what the capacity increase is, the high efficiency screens then allow us to be able to provide that without changing anything. So you can stay validated, your particle size not really going to change, but you have benefits associated with the high efficiency screens. I don't know if I went too fast or not. I think I'm on the half hour. I was trying to get it within the half hour. I hope that we've given you a small glimpse of some of the things that we've been doing over the last few years. And I don't know if you have any questions. I'm happy to answer any questions you may have.
Thank you. Thank you, Wilf. Sorusu olan var mı? Wilf'e soru sormak isteyen varsa sorunuzu iletelim kendisine. Çok teşekkürler. Özellikle online olunca biraz daha zor oluyor konsantre olmak. Thank you, Wilf. Thank you very much.
Thanks for having me, and next time we'll make sure